Hey, welcome back to Introduction to Computer Networks at NTU. This is once again Polly speaking. Yeah, as usual, let's go over the announcements, all right? And let's just skip the first two bullets from now on. Bullet 3. The assignments due this Saturday are PA2, quiz 6, 7, and 8. Okay. Again, we'll dynamically adjust exactly how many quizzes are due at the end of the week after the Wednesday session. All right. And hey, I got you guys' PA1 solution already. All of you passed. Okay. So there are a few, not many glitches here there, but you guys did well. But since this is the beginning of the class, you guys are probably trying to give, you guys are not quite yet familiar with the style of the course. So what I do is to point out issues and then communicate, okay, what we are expecting when we are grading. Okay, so PA2 will be due this Saturday. PA2 is a lot more complex than PA1. PA1 is straightforward, just so that you log on and do some Unix commands. So PA2 is available, and if you click into the channel, you will see that Polly actually give you guys posted a heads up, be careful. Okay, at the end of the PA2 description, you guys will need to download this code called pollys PA2. It's a binary file. It's a executable. You just run it. Okay, but it does not run on arbitrary machines or arbitrary systems. It is compiled on the PA server, so it runs only on the PA server. And the purpose of this this program or this file is so that after you upload your solution to the PA server, you want to run it and verify that it's working and it works as what me and the TA are expecting. So if you run pollys PA2 and the outcome matches exactly your outcome, then you'll be perfectly fine. So that's what the purpose of the PAs, pollys PA something are for. Okay, so for each PA, there'll be this binary file there for you to verify whether you get things right. All right, and you know what? As we are talking about PA2, PA3, you guys can start working on it already. PA3 asks you to write the client of a file upload service. So the file upload server is already running on the PA server. Okay, so download the pa3.pdf file, follow the description, and work on PA3 if you want to start early. As I mentioned at the very beginning of the semester, that PA3 is probably one of the hardest given the amount of background you have. Okay, so those who can wait, I see actually some teams, a few of you, not many, have already completed PA2. And hey, it's a good time to start PA3. Okay, never too early. All right, now let's go back to the announcement. All right, bullet 4. There's a Google spreadsheet available now, okay, which records your progress, the scores you receive for the 3 major components that you receive a score for the semester. One is what? Quiz, okay. The other, participation, and the last one is the PA, okay. There's also exam. Okay, but exam is going to be communicated in another way because the exam scores somehow for most of you are sensitive. Okay, so if you click into this link, it will take you to this file. It's a Google spreadsheet, and inside this file there are 3 worksheets. First worksheet is called PA. So you see that the PA1 are graded already, and all of you received the full score. But I did add some comments after reading your solutions, okay? And the second worksheet is the marking of the quizzes. So far we have completed up to Q5, and all of you have completed all the quizzes so far, and some of you are highlighted. So team 1, for example, for Q3 and Q5, you get a highlight. That means that you either are providing some fresh perspective or you're providing something that's thoughtful. And I'm sorry that these highlights are somewhat subjective. That kind of matches Polly's taste of what's refreshing, what's thoughtful. Okay, so usually that involves that you spin your brain a little bit more and come up with something surprising. All right, or you provide something that's coming really out from you. Okay, I can see it's very honest and sincere. All right. And then participation. So there are 4 categories of marks you earn for participation. So the first one here is the YT stands for YouTube chat. Okay. So the ones that are more chatty it gets higher score, but I would cap for every week to just 5 points so that you guys don't overdo it. All right, so I have a sense that this semester we have a very chatty group because I get many questions as we play the videos. So I'm capping it to 5. So participate when you feel that you want to, not because you want to max your participation grade. All right. And then there's a column called Slack. I should update this. What I meant is the score, because we used to do the class discussion thing on Slack, but then they started charging people, so I switched to Discord, okay, which is working just fine. And so this records the Discord participation. That includes how you type the solution on behalf of your team for the quizzes, or you ask a question here on the Ask Us Anything, or give a comment or helped answering questions on Ask Us Anything channel or random channel. You see that those who ask questions will receive points. Those who answer questions will receive more points. Okay, so as you recall right at the beginning, the style of this course is so that we are all equal. Feel free to fill each other's sentences, answer each other's questions, because that's what I find the most effective way of learning. So think about the internet today, right? Or think about using these AI tools today, right? AI tool is essentially a summarization of what's available on the internet. So people providing answer to your questions already, and AI is just somehow collecting them, organizing them intellectually. And of course, understanding your question intellectually. So knowledge is there because we communicate. You see? Communication is such an important thing to accumulate wisdoms, okay, knowledges. All right, and offices for participation during the office hour. So far, I guess this is just the beginning, and the material is somewhat straightforward. Although they can be a little bit tricky, but they are straightforward. But later on, then you guys might want to use the office hour in case there are more questions you want to ask. And some of you might prefer just type things up and send me emails. And some of you might just type up on Discord and do the Ask Us Anything. Okay, on the Ask Us Anything channel. Okay, all right. So this is week 1, and I've already recorded up to week 2, and every week I would update the participation scores. All right. Is there anything I want to say? Yeah, I think there's one more announcement. Bullet 5. Okay. So towards the end of the Wednesday session, and maybe the beginning of next week, we're going to talk about a protocol, a particular mechanism to allow secure transmission of data on the internet. And that mechanism uses a public key cryptography. It's a special kind of cryptography that encodes content so that it's transmitted like a secret. So anyone intercepted the message would not be able to know what's to be communicated between the sender and receiver. Okay. And some of you might not have the background of cryptography. So there's a series of videos Polly has generated, and just to give you an overview of how public key works. And there's an example that is the most basic public key crypto, and you get a sense of how it works. It's a asymmetric key system. Usually we use a key to open our door and the same key to lock the door. But public key crypto uses one key to lock the door, but uses another key to unlock. So the original key you use to lock the door does not unlock the door. It's a very interesting way of doing encryption to transmit secret. Okay? And it's very useful for secrets that needs to be communicated between two ends. You will see later this week or early next week. And that's all the announcements we have. Let's move on to the topics today. Here's a quick summary of last week. Essentially, last week we give a very high-level overview of internet and then start talking about the edge. And we know that there are two components in the edge. That's the end systems. And the end systems, a pair of them can communicate in client-server mode or peer-to-peer mode, which we will talk more about in the next chapter, chapter 2. And then we learn about these access net technologies. Right? There's a variety of them. We spend quite a bit of time talking about the mechanism and talk about the cables or the wireless cables used by these access net technologies. But mostly last week, we talked about the core of the internet. There are two very important philosophies. One is called circuit switching. The other is called packet switching. Okay, as Polly was asking in the pop-up queues on the live chat. Yeah, the pop-up queues on the live chat are also opportunities for you to get more participation points. Okay, and that is also an opportunity for you to refresh what we have talked about last week or last video. So in the core, we have these two different philosophies. The keywords for the circuit switching are what? Dedicated reservation-based and call setup time. So first two are the advantage. The last one is the disadvantage. Now, in fact, if you do reservation-based, each user only get a fraction of the bandwidth. And if the user is idling, then there's a waste of resource. Okay, so in circuit switching, advantage is that it's dedicated guarantee. The performance is nice, predictable. But on the downside, there's a call setup delay. There could be idle resource, okay, a waste of resource. But in packet switching, the keywords are what? Shared. But at any time, you can use the maximum capacity, okay? But on the and there's no call setup delay. But on the downside, we can have congestion when there are too many users sending too many data packets at the same time, right? So that actually adds delay. If you recall, there's something called queuing delay. Packets gets waiting in the queue, right? If you recall this term, statistical multiplexing, you see users, traffic coming in, if they come too fast and the outgoing link is not fast enough, then hey, there's this buffer space there and packet gets queued up and they wait there. Okay. Do you like to wait in a queue? None of us do. Yeah, so there's extra queuing delay, although there's no call setup delay. And then there's store and forward because there's no call setup. When packet arrive at the router, a router in a packet switch network needs to check the content of the packet, particularly the destination address of that content, so that the router can decide exactly which next link to go. You see, because there's no circuit set up already. It's not by default a router receive a packet and immediately knows where the packet will go next. Okay, so store and forward, statistical multiplexing, these can also be the downside of packet switch network. All right. And you know what? We're not quite yet done with packet switch network. So sometimes there was a quiz, if you recall, quiz, I think quiz 5. I asked you guys which one you prefer, right? I know most of you prefer packet switching because it's a better utilization of the resource. because hey, the world is in a state that the population is high and the natural resources scarce. Then you think that way, very natural. But there are some saying that I would prefer that if I have a serious job to be done, there needs to be some sort of guarantee so that there's no unexpected accidents. Okay, so some say circuit switching. So I guess which one is better? There's no slam dunk solution. It's a lot of times traffic dependent, and I think mostly user demand dependent. So what kind of data you're sending, and what are the natures of these data? Okay, so today the last video about packet switching is internet. We know already. I've already revealed that the internet is based on packet switching. So hey, packet switching does not do call setup, right? So you do not provide guaranteed service. What if you have a service that you want to make sure that the performance is guaranteed? You know what? There's a technique called virtual circuit one can implement on a packet switch network. That is the first part of the first video we'll be playing about. In the second half of the video, you will hear a taxonomy, a summary of all kinds of design models for a communication network in general. So this video, I think 3 minutes, okay? And actually in a packet switch network such as internet, we can potentially emulate a circuit-like behavior that is called virtual circuit network. So instead of looking at the destination field in the packet header, we look at a very special header field called the virtual circuit ID field. Okay, so there's a tag there, carries a number. Okay, that number determines which is the next hop. So inside a packet, there could be many fields in the packet header. One is called destination. There's another one called the virtual circuit ID. And one can look up that field and decide which is the next hop. And how do we do that? We'll talk about that also in chapter 4 and chapter 5. And what's nice about this approach is that we can then try to ensure, okay, all the packets for that stream traverse a fixed path. In a way, packet number 1, 2, 3, 4, chances high that they arrive in order. In this case, in case routes might change, if the later route is shorter than the earlier route, chances there packet 1 might arrive after packet 2. So, packet switch network. To sum everything up, this is general communication network. 2 different flavors depending on which philosophy we design the core of the network. If we are going for a circuit core, it's called circuit switch network. If we are going for a packet-centric core, packet switch network. In circuit switch network, we know there are different ways of dividing resources into pieces. Frequency division or time division. But either way, it's very regular following certain order. Things will need to be reserved. There's a call setup delay. It's good for long-lasting calls where you will prefer data not experiencing variation in delay, not experiencing losses. But this is very resource consuming. Each time we will not be able to allow many users going on at the same time. On the other hand, packet switch network, simpler, flexible, no idle resource, but we might have congestion. So that's this track, datagram network. We look to the destination network address and then decide which is the next hop to forward. And so we need to store the entire packet, and so they might get queued, and they might get dropped in case there's not enough space in the queue. But we can also try to emulate a circuit behavior using the virtual circuit tag, which allow us to look up into the packet header field that's a little bit faster and streamline the process more or less and maintain packet arrive orders. Packet switching versus circuit switching. All right, so that's the last about packet switching. The next topic is called the network of networks. that we actually mentioned this term already, this phrase already, because the internet, the physical look of it is a network of networks. We have small networks. For example, NTU is a small network. A company is a small network, and these small networks will somehow connect it to ISPs in the middle. All right. Now, so the next two video is to enforce such a visual sense of how internet looks like. Okay, and the first video actually talks about when internet just begins, when it's still a research project. How there's certain engineering sense into designing how the small networks are connected, interconnected. But gradually you see that as the internet gets more open to the public and commercialized, then there are factors such as economical reasons, such as government policies, will play bigger roles. Okay, so this is internet in the earlier decades.
Internet structure. It's a network of networks. Earlier we learned we have end systems at the edge of the internet. They're connected to the core through the access networks, which are part of these access ISPs. Now, some of these ISPs serve home users more. They're called the residential ISPs. Others serve companies and universities. They are more often being called institutions and ISPs. Well, either way, any two hosts in these ISPs wanting to send packets to each other, their access ISPs will need to be interconnected. As a result, we see a network of access networks. Over time, they grow pretty large and complex. And much of these growth is driven by the economics, and some of it driven by governmental or business policies. In the next few slides, what you'll be seeing is essentially the evolution of the internet. What I'm drawing here is a bunch of these access ISPs, or I call access nets here on this figure. Let me just omit drawing the end systems because there's just going to be too much of them and the picture gets too messy. So the first thing the internet engineers are thinking is this: how are we going to interconnect these guys? Well, one obvious way is, how about connecting them all? But as a result, you see there are n square connections. And when the internet grows, adding one more access net, we'll need to add n extra links. So this is going to be a very expensive thing to maintain. And so internet engineers go with the other extreme. Everyone connects to one global ISP in the middle. So data come here, and the global ISP transits the data for the access net to the destination. Similarly, here. So in a way, the global ISP in the middle here is providing transit services to the access nets, which are the customers. Now, as the internet grows, as the number of these access nets grow, then there'll be more paying for the transit services. Gradually, the global ISP will begin to see profit. And when business is profitable, you see competitors. So now we have not just one global ISP, but multiple global ISPs. So A, B, C here are three global ISPs. They're competitors, but unfortunately, they also need to collaborate. Because what? Just like the access nets needs to be interconnected so that they can serve the end systems, their customers. ISP ABC will also need to interconnect so that they serve their customers, the access nets. All right, so must interconnect. There are two ways for the global ISPs to interconnect. First is to establish peering links among each other. The other is to connect through these IXPs, Internet Exchange Points. Now these IXPs are special. They're typically set up by government fund or by the nonprofit organizations because it's kind of important that we have these, third company there maintaining the basic operation of the internet to avoid companies, commercial companies, to dominate. So that's pretty much the structure of the internet for a long time. But over time, we see more. So local communities such as this guy and this guy here can also grow. When there's enough number of these access nets around, we begin to see regional ISPs showed up. What these regional ISP is doing is this, offering lower price internet access to the access nets and try to negotiate internet access with the global ISP with a lower price. So hopefully the regional net here finds a margin of profit. So profit here and saving money here. For global ISP, this might not be a bad thing at all because it only needs to deal with one customer, which is the regional ISP, instead of multiple of them. Okay, so less overhead.
All right, so that was the look of the internet in the earlier decades. But in recent decade, there's one new player called the content provider joining the scene. So if you recall in the video that Poly uses big circle representing these big ISPs and they are at the center of the whole network. These content providers, they are actually at the edge like those small networks, access networks, but they are huge and they are spread out throughout the world. Okay, so in a way, how important these content providers are just the same as the ISPs. But where they are in the picture are actually more like the access nets. So pay attention to the next video.
And this structure has been there for a long time until about a decade ago. Content provider networks showed up. Let me talk about content provider network by example. So let me use Google here. It'll be easier for you to understand. So Google established these data centers worldwide. Okay. What they do is to go to access networks locally where the data centers are, and then ask to connect to the access network, their data center. Now, the number of machines they are maintaining there at their data center and the connections they are buying from the local ISP are actually comparable to the global ISP here. The entire infrastructure there at the content provider network is just as big as the global ISPs in the middle. But what's a bit odd is this. The content provider networks, they're actually physically at the lower level of the hierarchy. As opposed to the global ISPs, they are at the center of the hierarchy. Scale comparable, but where they are in the hierarchy, very different. All right. In the next picture, let me try to draw the network slightly differently so that you see where they are in terms of how resourceful these provider networks are. You see here then, the most resourceful one at the top, the least resourceful one at the bottom. So at the center, we have Tier 1 ISP and content provider network. Tier 1 ISP interconnect to each other through peering link, and they also connect to the IXPs. Content provider network somewhat different. They connect to the local access ISPs and IXP. All right. But keep in mind, this is not exactly absolute. Some Tier 1 ISPs might also have access ISPs connections. Google here, if this Tier 1 ISP offers a fair price, might also establish a connection. All right. Good. Now, the final slide is just to give you a rough idea what's inside a Tier 1 ISP. As I'm drawing here, it looks simple, but it's actually quite complicated. This is a Sprint's backbone. Sprint is one of the major operators in the US. It's also a Tier 1 ISP. Each of these red dots is called a POP, point of presence. So the row there is pretty much like a data center in Google. It's a rack of machines. In this case, a rack of routers. Okay, so rack of these routers. They're interconnected between each other, and they are also offering connections to the customers. And some of them might be connected to other tier 1 ISPs. And these links are to go further up into the backbone, in the hierarchy of the backbone in Sprint's network. And this is internet structure, a network of networks.
So you see, internet is a network of loosely, somewhat complicated hierarchical network. Okay, so hopefully you get a good visual sense of how internet look like. And you see it towards the end of the video that the physical connectivity can be really complex. Okay, good. And with that said, we finished talking about the core of the internet. Now we move on to the next topic called the metrics. That's chapter 1.4. Because the reason that the internet continues to evolve is because, hey, the user demand continue to grow. And all we care about are performances of the internet, right? So do I need to wait long to download something? Can you guarantee that my packet won't lose when I'm playing a shooting game? Things like that. So metrics. This first video overview the three metrics: delay, loss, throughput, and a review quickly again why we have delay, why we have packet losses.
Starting from here, we'll focus our discussion mainly on the packet switched internet. And 1.4 is to talk about the important metrics we care about designing protocols for it. That includes delay, loss, and something called throughput, which we'll talk about at the very end of 1.4. How do loss and delay occur? Well, let me draw your attention to the example below, that'll be easier. First kind of delay is happening here, in the packet that is going out, being transmitted out. That delay the packet is experiencing is called the transmission delay. That is the time it takes to transmit the packet, and we know how to calculate, don't we? It's packet size divided by the link rate. But there's a second kind of delay experienced by packets here before they get to go out. These are what? Packets waiting in a queue, waiting for its turn. And how can there be packets waiting in a queue? It actually happens quite often when the incoming rate exceeds the outgoing rate. So you see in the example, A and B sending packets actively together into the router. In case the aggregated arrival rate is higher than the outgoing rate here, then you will see there will be always packet here waiting to be transmitted, and therefore subsequent packets will need to what? Wait up. And that is queuing delay these packets are experiencing. Now the calculation of queuing delay is a lot more challenging than the transmission delay. It really depends on the arrival pattern before a packet comes into the queue. Okay, now if that pattern is reoccurring, predictable, then it will be easier to calculate this. Otherwise, very challenging. Now, that explains packet delays, where they might occur. Packet might get lost as well at the router, and it happens here. Focus on this thing here. It's the packet queue. The size of the packet queue is limited. Okay. By the way, that packet queue is also often referred to as the buffer. Okay, and the buffer space is limited, just like the memory space is limited. The buffer space is just a way of calling the memory reserved, okay, to store these packets. Now, given that the amount is limited, in case congestion persists for a long time, then eventually you run into the situation. There's no longer free buffer space in the queue. In that case, arriving packets will get dropped, and therefore we see packet losses.
All right, so that was straightforward, but hey, make sure you remember this. When there's queue, there's queuing delay, and calculation of the queuing delay can be complex. Just keep that in mind. Next, let's focus on delay. Okay, the first video is short to introduce the 4 components of packet delay.
Now, packet delay. There are 4 components. The first component is the nodal processing delay, but we just call it processing delay. It occurs right here when the packet arrives at the router. Router here checks the bit errors in case there's any, and decides quickly which output link the packet should go out. Next, queuing delay. That's the time the packet waits until it's turn to go out on the output link. So it occurs right here at the buffer space where packet queued up. But the amount of wait depends on the congestion level of the router. Component 3 is the transmission delay, and it's calculated this way. R being the link bandwidth, L being the packet length. And the time to transmit the packet out will be L divided by R. And it's happening right here at the interface between the router and the link. Final component, propagation delay. Provided the length of the physical link and the propagation speed of signals traveling the physical link, we know that the propagation delay is D divided by S. So essentially, the time for the packet to traverse the physical link. Be careful. S here is the distance the signal can travel per second. R here is the number of bits the transmitter can push out per second. Although I call S the propagation speed, R the link speed sometime, but there are two very different quantities.
All right, so now at the end of the video, you see what queuing delay, Polly just said that it's complicated, not that easy to compute, but transmission delay and propagation delay, these two other components, hey, there are formulas for them, all right? So next video is to give you a couple examples, okay? And ignoring queuing delay, ignoring the processing delay, we calculate the packet delay.
Right? Now let's go through a couple examples to exercise calculating transmission delay and propagation delay. What you're seeing here is a caravan of 10 cars. Now the way to think of this scenario is this. Think of cars being bits and caravans being a packet. So we have a packet containing 10 bits in a sense. The cars will be propagating at the speed of 100 kilometers per hour over 100 kilometers, reaching the second booth. Toll booth number 1 here takes 12 seconds to service the car. All right. Question here is asking how long until the packet is lined up before the second router. All right, so transmission speed, transmission delay plus the propagation delay. So what is the transmission delay? We have 12 seconds serving per bit, and then there are 10 bits. So the time to push the entire caravan out of the toll booth is 2 minutes. And then the propagation delay is for the car to travel 100 kilometers. So 100 kilometers dividing the propagation speed. So we have 60 minutes here. And so altogether, 62 minutes before the entire caravan to reach the second toll booth. So you see, in this case, transmission speed, very fast. Propagation speed, slow. In the second example, the configuration is slightly different, mainly propagation speed and transmission speed. Propagation speed now goes really fast, but transmission speed much slower. So question here is asking, will the first car arrive at the second toll booth before all the cars are being serviced? Let's see, when will the first car arrive at the second toll booth? So transmission delay, 1 minute. Propagation delay, so we have 100 kilometers, but we're traveling 1,000 kilometers, so we'll be spending 1/10 of an hour propagating, and that's 6 minutes. Together, 7 minutes. So the first car will spend 7 minutes before arriving at the second toll booth. Now, 7 minutes is also the time to service 7 cars for the first toll booth. That means we have 3 cars that are still behind at the first toll booth. So yes, okay, when the first bit arrived at the next router, there could still be bits not yet transmitted out from the previous router. So in this case, where the propagation speed is really fast, transmission rate very low, you had this weird situation.
Yeah, so sometimes propagation is the bottleneck, sometimes transmission is the bottleneck, depending on the propagation speed relative to the transmission speed. Right? Now, next video is actually to sum up the 4 components. Now you know how to calculate the transmission part, the propagation part. The next video, you will hear that we usually ignore the processing part, the processing delay, because that's doing like checkup that's really fast. It happens like in a nanosecond or something like that. So we kind of ignore the processing delay. But queuing delay is not negligible. Okay, and you will get a sense of how queuing delay calculation can be challenging in this video, about 3 minutes.
Good. Let's sum up packet delay. So there are 4 components: processing delay, queuing delay, transmission delay, and propagation delay. Transmission delay, very low, typically microseconds. We just ignore the processing delay when we calculate packet delay. Transmission delay, propagation delay, very easy to calculate. L divided by R, this quantity is often significant and especially the case for low speed links. Propagation delay, slightly harder. It varies quite a bit from microseconds to hundreds of milliseconds. So this extreme is for satellite links, for example. We've seen earlier, it could go up to 200 or even more milliseconds. Sometimes the transatlantic or trans-Pacific links, very long optic fibers, could also take up to 100 milliseconds. Now, in the process of calculating packet delay, the hardest component is this, queuing delay. Now, it's very hard to calculate accurately because it depends on the congestion level at the router. Just to give you a sip of how hard it is, let's define again, R being the link bandwidth, L being the packet size. Let's add one more variable, the average arrival rate. So L multiply A is the average bit arrival rate. That is also the incoming traffic rate. R is the outgoing traffic rate. So we could define traffic intensity being LA divided by R. So when that quantity is close to 0, that means incoming rate very low, outgoing rate very high, then no bits really need to wait. So queuing delay very small. And it's depicted here. When LA divided by R is very small, queuing delay also very small. The other extreme is here. When the intensity is greater than 1, that means there are more bits coming in than more bits going out. And when time goes on and on and on, the newly arrival bits will need to wait longer and longer and longer. And it's pretty much here, approaching infinity. Now, when the intensity is between very small to 1, delay is simply growing. And as we will be approaching infinity, you see that the curve grows quickly like that, okay? Close to an exponential trend. So hard to estimate queuing delay. In fact, it takes a whole semester for a professor to teach about how one calculates queuing delay. And at the graduate school, there's advanced queuing delay that one can also take to make sure that you do a better job, okay, estimating queuing delay for highly dynamic incoming traffic.
All right. So, but I can tell you, yeah, it takes a whole semester to learn how to calculate queuing delay. But I can tell you that essentially the formula of the queuing delay depends on how the data arrival process look like. Okay, good. Now, last video is to just show you that how one can measure delay, okay, in practice. The video is a bit long, almost 5 minutes, but pay attention because what? Quiz 6 is exactly about how you measure packet delay.
All right. So that was the theory part of the packet delay. One can also find out what is the real internet packet delay by trying out this program, traceroute. Okay. What it does is to measure delay from a source, one hop at a time, all the way to a destination. So this is what I'm drawing here, source to destination, and it's sending 3 packets, one at a time, to reach each of the routers along the way. So router there receiving such a packet would return by sending a reply back to the sender. Now the sender there can time the interval between the transmission and receiving the reply and gets one estimation of the round trip time between the sender to the router. So it works like this. 3 probes to the first router, 3 round trip time estimation. 3 probes to the second router, 3 round trip time estimations to the second router. And this goes on and on until it reaches the final destination, and then the trace route program stops. The output of the program looks like this. This is an example. Trace routing from Gaia, umass.edu to Oracle France. So this is saying first hop router's name is cs-gw at IP address 128.something.something.something. And there are 3 round trip time estimations, 1 and 2 milliseconds respectively. What's a little bit interesting is between hop 7 and 8. There, you see at hop 7, round trip time was about 22 milliseconds, but suddenly to hop 8, the delay is about 100 milliseconds. So that is the transatlantic links connecting from US to Europe. A little bit more interesting is also hop 17 and 18. You see stars, stars, stars. That means the routers are not responding. Okay, and it could be because the probing messages are lost or the replying messages are lost. But it's more likely that the router is turned off replying to these. Routers are on, but the routers turn off replying these probing messages. Well, let's try, sending a trace route ourselves from here. How about that? Let's go over to a terminal and then trace route to say Google. How about that? All right. Good. First hop router. Well, it didn't tell me the name of the router, so chances high that the router doesn't have a name. Okay. Delay reasonable. 10 millisecond, 3 millisecond, and another 3 millisecond. Router 2 here, well, either the probing messages are lost or router turns off the functionality of returning to trace route probes. Now third hop, 30 milliseconds, suddenly much higher. Okay, fifth hop, delay not much higher than the third hop. And you see here, when it's star, 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 it takes longer time. It's because when the traceroute program sends the probing packet, there's a timeout interval. Traceroute will wait until the time exceeds the interval. Then it determines that, hey, the router is probably not going to respond anymore. So forget about the first probe, send the next probe. Next probe waits also some amount of time. Timeout, give up, and then sends the third probe. Okay, good. Finally, we reached www.google.com. But the name is actually quite different. TSA something something. Interesting. And the end-to-end delay, end-to-end round trip delay to www.google.com is about 20 something milliseconds. Now, something that's very odd is here. Hop 8. If you look closer, we do have 3 round trip time estimates. But each time, number A here along the way, the 8th hop, is slightly different. IP address is 101, 49, and 97. So you see here, packets, although going to the same destination, coming from the same source, as they go on the internet, the routes could actually change. Also, you see, hey, the time it takes to reach hop 5, 30 milliseconds, but the time it takes to reach hop 12 is only 20 something seconds. So the load of the internet changes also over time. So sometimes when you are probing to a closer router, could take a longer time because it was busier there. But when the traffic load drops and when you're probing a router that are farther away, you could get a shorter round trip delay. Yeah, very curious. And let's go back to the slide. And it turned out that it's a good time to start the next quiz.
You know what? It's a good time to start the quiz, but we don't have time for the quiz. So quiz 6 is going to be the first thing tomorrow morning. Okay? And with the remaining time, let me answer Sam's question. So Sam had 2 questions. One was earlier, talking when we were still summarizing packet switching, circuit switching. There's another kind of platform that is message switching. Okay, message switching. If you look at the upper right corner, Golan now is just the result of Googling message switching. Prob loss. Okay, good, Brian. Yeah, is trying to answer the question. So message switching is this. It's an ancient design philosophy. It is still implemented. Think about the postal system. The mailmen are carrying letters, documents still. Okay, from postal office to another postal office, think of these postal offices are routers, and eventually to the receiver of the letter. So it's an ancient technology. It's not electronic though, but in terms of philosophy, designing a human communication network, message switching is actually one of the earliest, okay, idea. Now, circuit switching, like build water pipelines and streamline the water. That's actually a little bit later. And packet switching is because building pipeline, it's very costly. See? So people come up with something that's kind of in between message switching and circuit switching. Lower cost and yet efficient. Okay? Same, I hope I answered the question about message switching. Good that you Googled this up. It's all related. And the second question was, what's probe lost? Yeah, because in traceroute it sends 3 probes for each hop. And these probing messages can sometimes be dropped. Okay, and the reason they are dropped could be because, hey, there's a queue, and because the queue is full, therefore the probing message is dropped. But it can also be that the router you are probing turn off the ICMP protocol, which is how these probes are implemented on. The protocol the probes are implemented on. So the next hop is just dropping ICMP messages and not responding. Okay, and why do routers do that? Because security is a big thing on the internet today. If you allow probes, it allows also hackers information to know more about you. So some routers, some servers, actually, we just drop the ICMP messages entirely, just allowing people exploring that part of the internet. Okay. I think Brian is saying because the traceroute sends a message to the server and expect a reply but didn't get it. Yeah, that's a probe loss. Thank you, Brian. Mahmed, do you know deadline of each PA, especially for PA2 and PA3? Yeah, I think that's one of the things I want to communicate. This is the course page. You see cover is back. If you scroll down, you see a schedule. If you click in here, you see the PA1 due date here, PA2 due date, PA3 due date here. If you go back to the very first video, first week, the second video, the Wednesday session, you will see also Polly flashing through the schedule of the semester. Then you get to see when is the due time for each of the PAs, and you get to see the time for the exams. Okay, we do have 3 exams, all right? Make sure you check all these deadlines. May I ask, the function of measuring delay of packets is really depend the current traffic, right? Definitely. Henderson, you are actually going at what I want to test you guys about in quiz 6. Henderson, wait until you work on quiz 6. Then you might be able to answer your own question. Okay. I think the deadlines are mentioned. Thank you, Henderson, Wei Lun, and Kang Shuo. They are trying to answer Mehmet's question. Yeah, Stanley too. Thank you. And Louis, no, I think about it. Is this problem in part related to? You know what? At some point in time, an ICMP-based DDoS attack was popular. But nowadays, because people kind of turned them off, so it's not an effective attack. So most of the DDoS attack targets this place. The DNS server, which we will talk about in chapter 2. Because that's the first server you access before you access the rest of the internet. All right, good to see you guys curious about the internet, all right? And you know what? And I think also, if you don't know where the PAs are, click into the golden link. You see PA1, PA2, and there's the PDF description from this link and the walkthrough video. So if you have trouble just following the written description, definitely play these videos and you might see that, the answer you're looking for right there. Okay. So think of these PAs as self-exploratory tiny little projects throughout the semester. And I think some teams actually walked all the way to PA6. I don't know how they did that. They probably programmed a server first for their own client to connect. Okay? And those who finished already PA6 is probably waiting for Poly to send the certificate for the secure web server. Okay, and guys, thank you for the many questions. I have to say that this semester, the lecture progress is slower than the previous ones. But it's a good thing. Think of it this way, that because you guys follow the lectures, follow the videos very well, so you have questions. You want clarification. And Poly is taking time to answer the questions so that we will be clear throughout the semester. Okay? And maybe at some point in time, when you are more familiar with the jargons, the terms, then let's see if we could go faster. You already see Poly playing the videos somewhat faster, probably 1.1 times faster. Okay? We are already trying to speed things up. Okay? So tomorrow, we will start from quiz 6 by Poly introducing quiz 6. With that said, hey, we are again over time. I say goodbye. Okay, guys, go to the next course. Bye. Thank you, James. Bye. Bye then.